Hi, Roshan. Thanks for joining. So we would like to
Hi.
discuss about the principles to create AGI, that is artificial general intelligence, and pass the Turing test. So I'll just explain briefly
Okay.
what is Turing test. Then I'll go on to describe what AGI means and what AI means. If you are new to AI, I'll explain in a brief manner. So Turing test is something devised by Alan Turing, who is considered as the father of artificial intelligence. So he devised a mechanism where the judge, the person who's asking the questions, should not know the difference between the machine and the human being. So let's say the judge is asking questions to a Turing machine. The machine should answer in such a
Okay.
way that the judge thinks that he's a human being who is answering his questions. So the judge
Okay.
would be
Like so
blindfolded.
it's like
Yeah.
vote is not it is not written or something. Understand.
Yeah. So the judge would be blindfolded. He'll be in a different room or something like that. And he'll be just asking questions. And the Turing machine would be responding to his questions. And if he finds it suitable, in a sense, if he thinks that the Turing machine is answering like a normal human being, that means we have passed the Turing test.
Okay.
So now that is the objective now of all this work which we have done. And let's go ahead and see what we have got today. See, the agenda for today's discussion is what is the problem? So it starts with a problem definition. So problem definition, then solutionscape and avenues in the sense of how it can be used for further expansion, principles involved, creation of the solution and future expansion. And I'm requesting the audience and the viewers not to confine themselves and to have the free flow of thoughts. To add on this to this concept, the other day we were discussing about the thought field, right? Thought field, thought spectrum.
Yes.
Yeah. So I
Correct.
found out
Last time
something. Have you encountered deja vu? You know deja vu, right?
yeah, deja vu.
Deja vu in the sense you tend to experience a phenomena where you feel that the such an happening is happened to you earlier. In a sense, you see someone walking, or you see the tree swaying or something. You feel that that particular event has happened in your past.
Correct. Yeah, we do get sometimes like that moment. Yes,
So
that's
that is
right.
deja vu. So how does that happen? That can that there are two definitions. There could be two reasons for it. One, the same happening has happened in a parallel universe. The same happening has happened in a parallel universe, and we are experiencing in our current universe, and we don't know how it has happened and how it has how it is the event is transmitted from that universe to this universe is through thought waves, through the thought
Okay.
spectrum, because there is no other spectrum which could travel across universes, across parallel universes. So this would help in bridging the gap in understanding quantum mechanics, in the sense they always have this problem of this observer and measurement paradoxes. So what happens is you observe something, something else happens. You measure something, something else happens. So that's the paradox of all quantum mechanics. So now what happens is if you bridge that with thought waves, you say that deja vu in a different universe, at that point of time, you have not observed. You are not in that universe. You are in this
Correct.
universe, but you have measured it. You have measured it through your thought. So if you extend this, and if you extend along with the quantum field, I guess we could solve the hidden aspects of quantum mechanics. So we'll discuss about that in a different presentation. So now let's concentrate on our presentation on AGI and how we pass the Turing test. And the reason why I'm talking about deja vu and thought wave is don't confine yourself. Don't confine yourself to a predetermined approach of thought process. Now, what is the problem definition? the problem we have at hand is the existing AI systems lack generalization, as in the decision making is in new scenarios different to a great extent from the pre-existing scenarios, pre-trained scenarios is not good. See, let's say you go to a new city. You are in Bangalore. You go to, let's say, Hyderabad. You, with minimum information, you are able to traverse along the city. You are able to navigate all over the city. That's because you have a similar picture, a similar layout of cities when you have been living in Bangalore. So you'll learn that all cities would be similar. The layout would be similar. You'll get a bus in the bus stop. You'll get a train in the train station, and you. So that is all natural. So that layout, that understanding, you are there. So that is your learning. But imagine a computer or machine is going to Hyderabad. It can never do the same way which the way you have navigated. It can never navigate like you.
Correct.
It has to be fed all the maps of Hyderabad.
Yes, like even for the artificial intelligence, the model they needs to get trained.
Pre-trained.
Once model is trained, then only pre-trained, then only it works.
Pre-trained, transfer learning, and all those things. I'll discuss about that when we talk about the training procedure which we are innovating. Yeah. So pre-trained approach, programmed approach. That won't help, because let's say you have 100 smart cities in India, and you ask a robot to navigate all the 100 smart cities. You will have to feed the map of all these cities to that robot. That's not good. Yes. That's the tedious, time-consuming activity. So the same happens with all the housing websites. The same thing happens with all the navigation data which Google has or something. They will have to feed the data for each city. They have to do everything from scratch. So that is the normal artificial intelligence which we have currently. So imagine we have artificial general intelligence which generalizes stuff. So it's like a baby. A baby learns very fast. That's because it generalizes very fast. The baby, infant, and early childhood stage, where during that early childhood stage, people learn very fast because they generalize very well. The only reason they are not as intelligent as the scientists is that they are not able to articulate. If they are able to articulate at that young age, then they'll be equivalent to the scientists, because their learning curve is very high. So that is what we are trying to implement using our AGI systems. That was this suggestion was given by Josh Tannenbaum of MIT in a webinar, and which was broadcasted by Lex Friedman. He is a very good person in this field and expert in this field. So if you see that webinar, you will see that towards the end, Josh Tannenbaum says, you will have to think like a child, think like a baby, infant, and realize artificial general intelligence. So that is what we are trying to do, and we are trying to accelerate that learning using biological Turing machines. Okay. So what is the solution scape and avenue which we are having? We are using biological Turing machines built on the principles of protein synthesis. So we have the neural networks, the synaptic connections, and all those things going on for the artificial neural networks which we have, and convolutional neural networks, and other for deep neural networks. It all uses the synaptic connections and the input, output, and hidden layers. And the number of hidden layers you have, the more number of hidden layers you have, the more deep is your network. So this is a pretty simple construct, just a 3-layer construct. But if you go for protein synthesis concept, you will have 6 layers. You will have 6 elaborate layers, and 3 basic functionalities. One is DNA to mRNA, mRNA to amino acid. So DNA to mRNA is transcription, mRNA to amino acid is translation. Yeah. So this is the process. Now, we have this concept of phenotype variation. Phenotype is gene expression. So let's say why is the eye color of some people are green, some people are blue, some people are black, brown, and other things. That's a phenotype variation. That's a gene expression. That's due to environmental factors, genetic factors. Less genetic, more environmental, you could say, phenotype. But eye color is not a good example. There could be other factors like health, lifestyle, lifestyle and nutrition based genetic factors, and your health. So that is like a phenotype expression, you could say. That's a phenotype variation based on your environment. So less of genetic impact and more of environmental factors. So there comes this field of social epigenetics as well. Social epigenetics is exactly that. So you have good vibes. You have good vibes in your environment. You are doing good. Your body feels good. Your health is good. So that is vibes and social epigenetics, and phenotype expression is also part of it. So now this phenotype variation happens when there is a transcription error. So what happens is from DNA to mRNA, when there is an error, even God does errors. So the natural process, even there are errors in that process. So that is an advantage for us. Why it is an advantage? You have variations. So once you have variations, you will have many states. And once you have many states, you can build a beautiful computer, which is very powerful.
That's right.
So the binary state computer has just two states, 0 and 1. So with that, we are doing all the operations for the past 60 odd years. So we have been talking about quantum computing, which uses the principle of superposition, but it's slowly coming up in infancy. But the DNA computers, it was in the talks in 2003, and that time they thought it would be very difficult. But now it's difficult with all the transcription modeling approaches. It is possible, and we could have a phenotype variation based DNA computer. So I'll talk about that later. Now I'll talk about transfer entropy. So what is transfer entropy? Okay, before going to transfer entropy, what is entropy? Entropy is the presence of randomness in a system. So the more the entropy you have in a system, more randomness. The more randomness you have in your system, you have scope of better definition, and in the sense, that is how the whole universe works. So the randomness keeps on increasing. So that is why it's getting difficult for us to define. But now this gives us an opportunity to introduce the surprise element. So we have information transfer, and we have transfer entropy. So we don't know what happens the next moment. So what opportunity this gives for our AGI system? What does a surprise element give to our AGI system? It gives the opportunity to learn very fast. It's not a pre-trained approach, a fixed path or something. So you have an entropy in the system. The system is able to adjust to the entropy. It is able to learn. That means it has generalized properly. Okay. So these three principles. One is the protein synthesis, elaborate process. Second one is the transfer entropy. AGI. And the third one is the phenotype variation. So all three principles would give us the AGI system. And this is the solution matrix which we are talking about. So the solution matrix has phases or principles, and also the principles which are in terms of a primary principle, working principle, guiding principle, and your working model or the scope for expansion. So now, what is the first phase? The first phase is you have to reach perfection. We are powered by Swarm AI. Perfection in the sense, you should have a good curve fitting first. So you have set of points, and you'll have to have a good curve fit. So you'll reach the perfection using Swarm AI. In the sense, Swarm AI is like individual intelligence. So you have individual points, let's say individual points. How do you draw a straight line? A straight line is a connection of dots, as a single individual points. So you will have to fit the curve, and each individual point will act as a swarm device. And the swarm device through its intelligence will give a correct path and you'll reach the perfection. So that is, and we should avoid overfitting by a generalization technique. So that is the second phase, and that gives the opportunity for a cost function. Okay, in the first phase, when we have a swarm AI based curve fitting approach, we also have this transfer entropy, which gives you the generalization as well and the surprise element. And the second phase, that is your working principle, is a cost function, which is based on your reverse transcription error. So I'll tell you what is reverse transcription. You have taken a photograph, let's say, or you made a 3D model of a person.
Okay.
Now you're reconstructing the person back from the 3D model. I'm just trying to bring an analogy. So it will not be possible. I'm just trying to bring an analogy. So you made a model of a model of a person. Yeah, like you went to Madame Tussauds show, like or Madame Tussauds place, and you saw a model of a live person, a celebrity, and you are trying to reconstruct the celebrity out of that model. So that is reconstruction. So now that is reverse transcription here. So transcription is from DNA to mRNA, and reverse transcription is from mRNA to DNA. So if there is an error in that reverse transcription, then you will have this cost function. So what is a cost function? A cost function is an error which we are trying to correct. So all artificial intelligence, all machine learning is based on the concept of reduction of cost function. So how we do about that reduction depends on the methodology we are using. We could use gradient descent or other methodologies, but we try to avoid gradient descent because gradient descent has the problem of various hyperparameters, and it has to be tuned. Especially the learning rate is a very tricky hyperparameter. You never get a proper learning rate because it depends on, let's say you have different people, hundreds of people studying the same subject. You will have a different learning rate. The person next to you will have a different learning rate. The time taken for you to converge to the ultimate knowledge is different, and the time taken by your neighboring person to converge to the ultimate knowledge is different. So here the ultimate knowledge is the max global minima. That is local minima and global minima. So global minima is the ultimate knowledge. So what is minima? Minima in the sense minimum error, minimum cost function. So that is your global minima. It's like a trough. So you have a mountain. You have a contour of different circles of various information. You have a contour. So you're traversing through the contour, and you have to go to the trough which has the minimum cost function or error. So that is your global minima. While you're going to the global minima, you will encounter local minima as well. So they will have to. Then the global minima is the place where you have minimum cost function, and that is where your prediction and your actual values almost coincide. So that is a gradient descent, and that is going to be used in all algorithms, machine learning, and artificial intelligence. So now we are trying to change the cost function by means of a reverse transcription error methodology. And I'll tell you, the reverse transcription error is not that great. So what is the advantage of having such a mechanism instead of the gradient descent? Convergence to the ultimate knowledge is faster. Convergence to the ultimate knowledge is faster, and errors are less. Learning rate is not required. Other hyperparameters is not required. You reconstruct the person very fast. So let's say you have to train for 10 hours. You will have to train for 10 hours to reconstruct the person in the normal training procedure with all batch processing and all those things, samples and all those things. You have to do 10 hours with so many epochs. Epochs in the sense how many, one epoch will have so many batches and so with so many epochs, you're running for 10 hours or one for whole day, and you're doing a deep learning training. You need a lot of data. because it cannot understand properly, because only if you have a lot of data, your accuracy will increase, and the accuracy keeps on increasing with every epoch. That's how the normal artificial intelligence or deep learning training works. It increases with each epoch, so it's a tedious process. Now, if we have a reverse transcription based reconstruction, the error is very less. The chances of getting back the image, getting back the model, the original model, the reconstructed, let's say, image, you're doing object, let's say, object detection, you're getting the reconstructed image is very fast. Because you just need one image. The reconstruction error, reverse transcription error is very less. You'll get a confidence of 95%, even if you have a reverse transcription error. So confidence of 95% is good enough for your object detection.
Yes.
So what happens with that? You just need one image. You're able to generalize as well. You have added entropy, you have added other means of making it to generalize. So you gave a Honda car, you gave Honda CBR, Honda CBR or other vehicle for your reconstruction, and you gave Suzuki Hayabusa as the one which you're going to detect, but it detects that it's Suzuki Hayabusa because the entropy has been added, generalization has been done. So Roshan, what I'll do is I will cut this call and I'll reconnect again.
All right, sure, no problem. Okay, all right. Thanks. Okay.